what is a derivative? Well, if you have a single variable function f, the derivative is another function. And it's another function that we define by this formula right here. We use this notation, f prime, to indicate this derivative function. To better understand this, let's take a look at what goes into this expression. You'll notice that we're looking at the values of the function at x and at a nearby point x plus h. Notice that the denominator is the difference of those two x values, and so we think of the denominator as being how much x is changing, how much the input to this function f is changing. On the other hand, of course, you'll notice that the numerator is how much the output of the function is changing, so how much f is changing itself. And with that in mind, notice that we can rewrite this expression as that. So it's a limit of the change in the output of the function divided by the change in the input of the function as that input change approaches 0. Okay, so that's the definition of what a limit is. Now let's ask the natural next question, which is, why is this interesting? Why are we interested in derivatives? What can you do with derivatives? And it connects to a lot of different natural things. So some natural starting examples. We'll start off with looking at the graph of a function. So specifically, keep in mind the graph of a function described by this equation. And so height, right, the y-coordinate, is used to represent the value of the function, f, and thus we have some curve. Okay. Well, now let's look at our definition of the derivative. It says we're looking at the values of the function at time x, and then some time later x plus h, right? And looking at those 2 points, delta x, how much x changes between those two values, is that width, that base of that triangle, and then delta f is the height of that triangle. And what we see then is that the delta f over delta h is the slope of that line. That divided by that is the slope of that line, and this is what we call a secant line. Now, this is for some small value of h, where we've got an actual displacement there between these 2 points. So keep in mind what the derivative is. The derivative is what happens in the limit as delta x approaches 0. And so looking at this picture and realizing that we have this point at where the input is x, this point where the input is x plus h, as delta x approaches 0, as h approaches 0, this point approaches along the curve and gets closer and closer to x, and that means that these secant lines are getting closer and closer to what we call the tangent line. And the tangent line is the line that you can think of as sort of just side-swiping the curve at the point in question, as I have it drawn here. Okay, so we're looking at slopes of these secant lines, right? Delta f over delta x is the slope of those secant lines. And then in the limit, as we get closer and closer, in that limit, we get the slope of this tangent line. Okay, so that's one way of thinking about derivatives, is that they give you the slope of the tangent line to the graph of the function. Okay, that is one interpretation. Now, critically, note that this makes sense only when you're looking at the graph of the function in question. Now, importantly, sometimes you aren't. Let's consider another scenario where you have a function that represents position on an axis as a function of time. So here we're not looking at the graph of this function f. Position is just represented by where you are on an axis. And we think of this position as changing at different times. So here's where we are at time t, right? And then some small amount of time later, some time h later, we're at time t plus h, and we're at this point there. So with this picture, not a graph, just thinking of the function as representing position as a function of time. Now what does the derivative represent? Well, if you look at our picture here, and you see that we have this distance, this displacement here, right? F of t plus h minus f of t. In other words, delta f is just that displacement. What's the difference between where I am now as opposed to where I was h seconds ago? Okay, so what then is this fraction? Well, that's displacement. I can see as the numerator, right? This denominator we don't really have on the picture. We're not drawing the t-axis on this picture, partly because we're not looking at the graph. So we can just think in terms of physics, though. Displacement, delta f, our numerator here is displacement, divided by time, the amount of time it takes to do that displacement, simply gives you average velocity. That's our definition of average velocity in physics. So displacement per unit time. So now that is, again, when h is small. This is for some small value of h. So what happens in the limit? What happens as h gets smaller and smaller? Well, instead of getting the average velocity over that piece of displacement, or that piece of displacement, or increasingly shorter little bits of displacement, we're taking the limit as delta t approaches 0, and in that limit we're taking average velocities over increasingly short amounts of time, and thus getting in that limit instantaneous velocity. So it's a very natural physical notion that can be modeled with derivative. The derivative in this point of view represents velocity. Importantly, with the assumption that we're not looking at the graph, but now the function represents position on an axis. So now let's go back to the graph point of view and make an observation about something you can do with the derivative, and that is that you can use the derivative to form an approximation of a function near a given point. So let's consider a scenario where we have a curve. This is our graph, y equals f of x. And we think about the tangent line. Here's our tangent line. And let's think of that tangent line as being a graph also. It's a tangent line of this function L. We'll come back and talk about what that is in a second. Okay, so this tangent line, though, has a nice feature, a couple of nice features. One is that tangent line goes through this point where it is tangent to the graph, and that point has coordinates a, f of a. So this tangent line goes through that point, first observation. Second observation, the whole idea of what we discussed a few examples back, was that the slope of that tangent line is f prime, the value of the derivative of this function f, specifically at the point A. Okay. So I know two things about this tangent line, and so we can write down the equation of the tangent line. It goes through this point, a f of a, and it has slope, that is f prime of a, and then you might recognize the point slope equation of a line from high school math classes is this. So there's our equation for this tangent line. And if you just solve for y, in this equation, to solve for that y, the remainder, thinking of that as this function L of x, we have this. So in particular, note that the graph of this function L is our tangent line. Okay. So that's where this L of x comes from. That L of x is this function here. Now, what role does this function L do? Well, you look back at this picture and realize that what this means is that for points x that are near A, the whole idea of this being a tangent line is that it is actually doing a good job of staying near the graph of the function we're interested in. Or said differently, the value of the function, the value of this L function and the value of our original function are very close to each other. Said differently, L is doing a good job of approximating this function f, and as such we call this function L, the linear approximation of the function at the point A.